Shift registers are serially connected flip-flops. They maintain shift bits of a code recorded in these flip-flops. That is why by clock signal, the contents of each flip-flop is rewritten to the next flip-flop. With each clock cycle, a code stored in a register is shifted by one bit, either to high-order bits or low-order bits. This feature accounts for the name of such registers. In particular, shift registers are used to shape pulses of preset length. You can set the pulse length with a control code. That is, pulse length is programmable. Let me show you the circuit of such a pulse shaper. In the initial state, before the input signal positive edge, a flip-flop is reset to 0. There are zeros at all the shift register outputs. There is one of the multiplexer's inverse output. A control code is applied to the multiplexer. Such code determines the length of an output signal. When the input signal positive edge is received, the flip-flop shifts to 1, and output signal is formed. The shift register begins consistently shift the signal on each edge of the clock signal. For example, the control code is set to 5. Then, when 1 is applied to the output 5 of the shift register, such signal will be transferred to the KP7 multiplexer's inverse output. The 0 signal applied to the flip-flop's input R will reset the flip-flop to 0. This means that the output signal will be discontinued. Thus, the control code determines the output signal length. The setting array is equal to 1 cycle of a clock signal. It depends on the time shift between the input signal edge and the edge of the nearest clock pulse. The greater the output signal length, the smaller the relative setup error.